And so now what we're going to look at is another efficiency, the mechanical efficiency. And this is the indicated work over the shaft work. And so this talks about how well the mechanical mechanisms work. So this is an indication of mechanism functions. So that's not part of this course. So that's a different course that one worries about that with. And so I could have the overall compressor efficiency. So this is the compressor efficiency. Eta sub c would be equal to eta sub cn times eta sub m, so it would be the theoretical work over shaft work. And so we can look at this, and we know how to find each of those. So for homework in this area, 16.47 star, 16.49 star, 16.51 star. And now what I'd like to look at is multi-stage compression, which reduces the work and improves the volumetric efficiency. So we're going to look at multi-stage compression. So it reduces work and it improves the volumetric efficiency. And it improves the volumetric efficiency because P2 is less, and so the lower the P2, the better the efficiency is. So now let's look at ammonia, which ammonia is used as a refrigerant as well. It obviously is toxic, so you don't want to breathe it, but it's a very effective refrigerant that's used currently. So for ammonia, so for NH3, K is equal to 1.304, and I'll do some calculations here and look at the multi-stage effect. So let's say that P1 is 14.7 psi. P2 is equal to 20 times P1, 294 psi. T1 is 0 degrees Fahrenheit, which is 460 degrees Rankine. And so now what we're going to do is find out what T2 would be. So it's just a way to look at what the compression would be. So now if I have a single stage compression, and then we're going to look at it compared to a two-stage compression. So I'd have the T2 over T1 is P2 over P1, N minus 1 over N, or K minus 1 over K. And so I'd have the T2 is equal to 460 times 20 to the 0.233, or the T2 is equal to 924.5 degrees K. So this is a single stage compression, and this would give me the discharge temperature coming out of that. So if I had one stage of compression, I had the intake, so I'd have it going in and going out. And now what we want to do is we want to have a multi-stage compression. So we'll have a cylinder here. We'd have it going in at 1, coming out at 2, going through the intercooler. Coming out at 3, going into the second stage, and coming out at 4. And in the book, it goes through the development of finding the optimum interstage pressure. And so I'm going to take the results of that. So what I'm going to do is that we look and we find that the optimum interstage pressure is, we saw that the P2 over P1, or in this case P4 over P1 is equal to 20. So what I'd like to find out is what is the best value for 2. So if I'm looking at this overall pressure increase, P2 for the optimum is equal to the square root of the overall pressure rise. And so that's shown, the derivation is shown in the text. It's mostly, I find people are not terribly thrilled to watch that unfold. So we have that T2 is equal to 460, the same inlet. And now P2 over P1, and this is 4.47. 4.47 times 0.233. So this is 652 degrees Rankine. And so if I look at this and I see a comparison, there's a big difference in the temperature that occurs. And so I'm interested in that. For this assumption, it assumes ideal intercooling. So it assumes ideal intercooling where T3 would be equal to T1. So this assumes well, let's say that T3 is not that, because that seems like it's an unreasonable assumption if I'm dealing with something cold. And so if I made T3 be higher, I can still find out what T4 would be. And so if T3 is equal to 50 degrees Fahrenheit, which is equal to 510 degrees Rankine, then T3 is equal to 510 times 4.47, 0.233, T4 rather. T4 is equal to 723 degrees Rankine. And so what we have is that the temperature is higher, but it's still much less than if I had one stage of intercooling. Let's see what this looks like on a PV diagram. So we'll go back and see what this looks like, and then we'll do an example with numbers associated with it. So on a PV diagram, and this figure is in the text, of course. And so what we have here is, this is the intake. So I have, this is the intake from the outside. Then we have the discharge of the first stage, which is the intake of the second stage. Then I have the compression of the second stage, coming back, and then I have the intake occurring. So this reflects what that is. So if I look at this, we have work at the first stage is n over n minus 1 times P1 times V1 minus V4, V1 minus V8. Have to pay attention here, David. Times 1 minus P2 over P1, the n minus 1 over n. And for the second stage, n over n minus 1 times P2 times V3 minus V6 times 1 minus P4 over P2 to the n minus 1 over n. And P1 times V1 minus V8 is equal to MRT1, and P2 times V3 minus V6 is MRT3. So what happens if I have the mass flow rate? If I have a mass flow rate, the mass flow rate stays the same. Your volume flow rate changes, but your mass flow rate stays the same. So, and I can obviously put dots here and have flow rates rather than that. And where I got that number, the square root of 20 before, if T3 equals T1, then if I take the derivative of the total work with respect to P2 and set it equal to 0, so what we're doing is we want the minimum work required, we'll find that P2 is equal to the square root of P1, P4. And that's where that came from. Let's do an example. So here we'll have a two-stage compressor. It receives 525 cubic feet per minute of NH3 at 1 atmosphere and 50 degrees Fahrenheit, and discharges it at 150 psia, intercooling reduces NH3 to 50 degrees Fahrenheit, so we have an ideal intercooler. N is equal to 1.26 and C is equal to 5%. And now we want to examine what this is. So let's examine what this is. And so if I draw a little sketch here, we have the first stage, we have stuff coming in at state 1, it goes through an intercooler, comes out and goes into the second stage, and comes out. So we have 1, 2, 3, 4. These are the various states that we want to examine. So what we look at now is we want to go through and find all this sort of stuff. And so the minimum power occurs when P2 is equal to that square root of P1 times P4. So the minimum power occurs when P2 is equal to the square root of P1, P4, the square root of 14.7 times 150, and so P2 is equal to 50 psia. The minimum power also means that W dot total is 2 times W dot of the first stage, or W dot of the second stage. So the minimum power occurs when the work here and the work here are the same, where I have this ideal intercooling occurring. And so if I solve for W dot of the first stage, it's N over N minus 1 times P1 V1 dot times 1 minus P2 over P1 to the N minus 1 over N. So this is 1.26 over 0.26 times P 14.7 times 144 square inches per square foot. So we have that to convert this to pounds force per square feet times 525 times 1 minus 50 over 14.7 to the 0.26 over 1.26. And now what I want to do, and I'll introduce this factor, I'm going to divide by 33,000, and I'll explain what that is. So the units on this are foot-pounds force. So the units on this term are foot-pounds force per minute. What I want to do is convert it to horsepower. So 33,000 foot-pounds force per minute per horsepower. I had to read my own notes, so it was a little difficult. So I get that, so if I divide by this 33,000, it converts this term, which is in foot-pounds force per minute, which is a big number if I'm going to divide by 33,000. I then get it down to a smaller number. So W dot of the first stage is equal to 46.9 horsepower. So W dot total is twice that, is equal to 93.8 horsepower. So this is what happened when I did this for 2 stages of compression. And what I did to be compulsive is I decided to do it for 1 stage of compression and look at the difference in power requirement and see what it is. So for 1 stage of compression, I have that W dot is equal to 1.26 over 0.26 times 14.7 times 144 times 525 divided by 33,000 times 1 minus, and now P2 is 150 over 14.7 to the 0.26 divided by 1.26. If I solve for that, I have that this would be W dot is equal to 100.3 horsepower, or about a 7% increase. So one of the things that we look at is the operating. 7% is a big number if you have to pay for the power that provides this on an ongoing basis. If you want to be the manufacturer to do it cheaper, then it's cheaper to have 1 stage of compression. You don't have the complexity of 2 stages, you don't have the intercooler, etc. And so the person who runs this would probably want to pay extra money to have 2 stages of compression because the operating costs are going to be less. if I look at the heat removed from the intercooler, so just the last thing, that if I go back now and look at the intercooler, we have that Q dot is equal to m dot times H3 minus H2, which is equal to m dot C sub P T3 minus T2. M dot is equal to P1 V1 dot over RT1, 14.7 times 144 times 525 divided by 90.3 times 510. So that's going to be equal to 24 pounds mass per minute. So that gives us the mass flow rate of the ammonia going through there. And then I can solve for Q dot. So Q dot is equal to 24 times 0.499 times 510 minus 656.5. And so Q dot is equal to minus 1754.5 BTUs per minute. I just wanted to check on something. And so what this is T2. And we can find T2, which I hopped over, but we can find T2. T2 is equal to T1 times P2 over P1 to the n minus 1 over n. So this is equal to 510 times, where am I? 150 over 14.7. I have to follow my notes correctly. 510 times 50 over 14.7 to the 0.26 over 1.26. So T2 is equal to 656.5 degrees Fahrenheit. And that's where that temperature comes from. So the intercooler, we removed this amount of heat, and because of that, the air was cooler going into the second stage.